Welcome to Calculus 1, Chapter 2, Section 2, the limit of a function. I'm going to go through some PowerPoint slides that came or were created in tandem with Stewart's Calculus book, 8th edition, props to Cengage, and we're talking about limits. And these slides were not created by me, but I'm going to go through and sort of talk through some of the problems, and I'm going to write over the top of some of the problems and attempt to clarify some of the topics and concepts and methods that are used in order to solve the problems in this section. And then I'm going to toggle over and cruise through the homework assignment that I'm going to be assigning to my students, just for them to clarify a couple of different ways that the questions are asked in the assignment, and to frighten them preemptively by showing them how much work is in their homework assignment. Alright, the following table gives values of f of x for values of x close to but not equal to 2. And it's this function that we're talking about. We're taking f of x from this page, which is a parabola concave up, and we're plugging in some x values over here in this column, and then they're generating some y values in the second column. We've got more x values, more y values, and we're working around the number 2. And my students are going to be doing this in their homework assignment. I say that my students are going to be doing this in their homework assignment because I don't know if someone's wandering around YouTube and is going to end up watching one of my videos. So I don't want my students to think that they're not special. First and foremost, I'm making this for you. The x values in this first column are increasing from 1, and then they're getting really, really close to the number 2. So those are increasing. In the third column, we've got x values that are starting at 3, and they're decreasing, getting closer and closer to 2. On the number line, if this is the number 2, and here's 1 and here's 3, the left-hand column is bringing us toward x values, or toward an x value of 2 from the left, and I say that very intentionally for a reason. And in the third column, our x values are decreasing, starting at 3 and working their way toward an x value of 2, but we're coming at that x value of 2 from the right. And we're going to be doing that multiple times in this lesson, and you're going to be doing it more than multiple times in your homework. What we're illustrating with this table of values is, in the second column, if you look at these f of x values, as our x values are approaching 2 from the left, so as we're working our way down here, what's happening to our y values, our f of x values? They look to me like they're starting at 2 and they're getting closer and closer to, maybe they're trending toward a y value of 4. Okay? And then in columns 3 and 4, specifically column 4, we have an f of x value, a y value that's starting at 8, and as our x values are getting closer to 2 from the right, it looks like our y values are trending again toward 4, except this time the y values are staying on the high side of 4. In column number 2, when we got to the bottom of that column, our y values were getting close to 4, but they were coming at it from the underside, I suppose, because they're y values. 3.99 is definitely below 4. So we're sort of squeezing our way in toward 4. And this is a graph of that parabola and an illustration of what we were doing with those x values. Here you can see the x values are coming in from the left. As we move to the left on the blue curve, we're swooping up toward this point, and starting at an x value of 3, here's the x value of 3, and as our x values are moving to the left, we end up sliding down this curve, getting closer and closer to this point again, which has a y value of 4. Now in the table of values that we saw, we never actually plugged in an x value of 2, and that's because when we're working with limits, we're not actually concerned with what's happening at the specific x value. I don't want to know what's happening when x equals 2. I want to know what's happening as we get really close to an x value of 2. Sometimes I'm only concerned with what's happening with our y values as our x values are approaching 2 from the left. Sometimes you'll specifically be asked what's happening with the y values as our x values approach 2 from the right. In which case you want to plug in an x value of 3 and then 3.5 and 3.2, 3.1, 3.001. I said that wrong. 3, 2.5, 2.1, 2.01, just like we did in that table on the previous slide, getting your x values super close to 2, but never actually plugging in an x value of 2. And that kind of an examination of this function is indicated using this terminology right here. We say that the limit of our function f of x as x approaches 2. Now the conversation that we had in this table we had our x values approaching 2 from the left and from the right. And in fact, that's what this notation is wanting us to do. This notation is asking us to check what's going on with the y values as we come at this x value of 2 from the left and from the right. It so happened in the graph that we were just looking at that the y values coming from the left and coming from the right were trending toward that same value of 4. At the bottom of column 2 and at the bottom of column 4, we saw that those f of x values got super close to the number 4. Will that always happen? At the bottom of column 2 and column 4, will our y values always be approaching or getting close to the same number? The answer is no, not always. And when they don't approach the same y value, we will say that the limit does not exist. But I'm getting ahead of myself. So here's the notation. The limit of our function f of x as x approaches a equals L, and L is the limit. Again, we're getting arbitrarily close to L. Extremely close. As those x values get really close to a, our y values get really, really close to L. I like this sentence right here. The values of f of x approach L as x approaches a. So that capital L, we're not actually even talking about reaching the value of L. What we're saying is that we're approaching the value of L. When? When x approaches a. We're approaching a. We're not arriving at a. We're just getting close. And I got some feedback from a student recently who said that sometimes my videos come through a little quiet. So I'm going to bump up the gain here a little bit more than I usually do. And that might push me into the red a little. But we're going to see if maybe that's helpful on your end for volume control, so you don't have to crank the volume all the time. Let's try that. An alternate notation for the limit. So this is, oops, got to turn my highlighter off. This is one notation, and another notation is this one. It's sort of the reverse of this method. So here that I've circled, this says the limit of our function f of x as x approaches a. Notice that I've already said as x approaches a. Sends our y values close to L. Here they're mentioning L early in the statement. So just be aware that you could see this topic or this request for a limit phrased slightly differently from time to time. So here are three really nice nice graphs for us to look at. And you can see that we have an L value on the y-axis, we have an A value on the x-axis. I point those out because those two values are inside of this limit statement. They're a component. Let's zoom in and look at this first illustration. This is a smooth, continuous curve. And let's talk about what happens to our y values as x approaches a. So maybe we start from here, and as my x values are moving to the right, that pushes me up this blue curve, and as my x values get really close to a, my curve gets really close to this point, which means my y values are getting really close to a y value of L. If I hop onto my curve over here to the right, and I start pushing that point to the left, it's going to come up over this hill, and it's going to start coming down, and as my x values get really close to a from the right, my y values again look like they're pointing at that same point right there, and that point has a y value of L. However, we're never actually arriving at that point. All I'm saying is that the y values are trending toward L as we push our x values in from the left and in from the right. This is the same graph as we were looking at a moment ago, except this function is defined as having some other y coordinate when x equals a. This point used to be up in here. That used to be solid, right? It used to be over there, but now it sort of fell out of the curve. So let's go through the same investigative process as we just went through in the previous graph. We'll hop onto our curve to the left of when x equals a. We'll start pushing our way to the right as our x values approach a from the right. We end up pushing this point along the curve, and it starts rising and rising, and our y value gets really close to L as our x value gets really close to a. And if we hop onto the curve over here to the right, and we start pushing that point to the left so that the x values are approaching a from the right, we find that this point comes sliding in here, and as our x values get really close to a from the right, our point on this blue curve is getting really close to that point that has a y value of L again. Whether we come at it from the left or from the right, we end up with y values that are approaching L. But when x equals a, we know that our function has some other y value down here. Does that matter? No, it does not, because I think I've only said this like 7 times already. I'm not interested in what's happening when x equals a. I'm interested in what's happening in the immediate vicinity of the point or the time when x equals a. But at least this function is still defined for x equals a. That's nice. Is that necessary? Well, here we're looking at the same graph yet again, except this function's not even defined where x equals a. And I am wondering, does that matter? And the answer is no. We push in from here, we end up aiming, as we come in from the left, we end up aiming at a point that has a y value of L. As we slide in here from the right, we're still pointing at or approaching a point that has a y value of L. And since I'm never going to actually get to that point, because I don't care what's actually happening at that point, we can still say that the limit as x approaches a of f of x is equal to L. So that's a true statement as applied to all 3 of these graphs. The limit of f of x as x approaches a does equal L in all 3 cases, whether your function is continuous, has a discontinuity at x equals a, or even if our function's not defined when x equals a. Doesn't matter. Do I want to talk about that? We'll talk about it briefly. The tricky part about this particular limit is that our x values are approaching 1, which in and of itself is not so bad. Except if you took the number 1 and you actually plugged it into this function, you'd find that you get 0 divided by 0, which is called an indeterminate form. I don't know if 0 divided by 0 is equal to 1, because anything divided by itself is equal to 1, or if the thing's going to blow up in my face because division by 0 means that the result is undefined. So this one's a little unusual. And there is algebraically a way that we could solve this, but we're still in this mode of creating a table of values. So here again, we've created a table of values where our x values are less than 1, but they're getting closer and closer to an x value of 1, so we're approaching from the left, and it looks like our f of x values, our y values, are approaching 0.5. It's a little higher than 0.5, but that's okay. And here we've got x values are greater than 1, but we're decreasing those x values, getting closer and closer to an x value of 1. And what happens to our function values? Looks to me like these are getting closer and closer to 0.5. A little on the low side, but that's okay. So as we come at an x value of 1 from the right, our y values are approaching 0.5. As we approached from the left, our y values were approaching 0.5. So we could say with a pretty good degree of certainty, especially since our x values we were taking those out 4 decimal places, I'd be willing to bet that the limit of that function as x approaches 1 is equal to 0.5. Will we ever be able to prove that with better certainty? Absolutely. It wouldn't hurt if you studied another dozen semesters of math, and then we could really talk about proving it. So example number 1, here what we have is the same function we were just talking about on the previous slide. That function is not defined when x actually equals positive 1 because of that 0 over 0 thing that I mentioned. So what this piecewise function g is doing is it's saying, well, let's define it. When x does equal 1, let's just say that the corresponding y value is going to be 2. Okay, so we said that as our x values were coming in from the left, that the y values were approaching 0.5. As our x values were coming in from the right, our y values were approaching 0.5. And then what this function g of x does is it defines our function when x equals 1 as having a corresponding y value of 2. Are we super happy that somebody finally came along and defined our function for when x equals 1, and that they defined it as some point that's floating up above the rest of the curve in that neighborhood? Not really, because again, I think I mentioned this once before. I don't care what's happening when x equals a. I don't care what's happening when x equals 1 in this case. The limit is still, in this case, going to equal 0.5. Whether my function is defined that x equals 1 or not. Don't care. Okay, one-sided limits. This is a little subsection that's all about coming at the point from the left or coming at the point from the right. So let's see what these illustrations look like. I even pre-drew a little illustration here for you there. Isn't it beautiful? I should have been an artist. This function, capital H, is defined. It's a piecewise function, defined as you see it there. And this text says that h of t approaches 0 as t approaches 0 from the left. Wasn't that super helpful? I don't like it. In fact, I don't like any of this. Not doing it. I already marked out that slide. I don't want to do that one either. This is the definition of a one-sided limit, so this is the kind of notation that we're going to use, and if we don't see another example problem as we're approaching from the left in these notes, when we toggle over to this homework assignment that I mentioned, we'll look at a couple. So what this says is the limit of our function as x approaches a from the negative side, but instead of approaching from the negative side, we just say as it approaches from the left. And that limit equals L. This is the sort of counter definition. Similarly, it says, oh, you can't see it. Similarly, it says, the limit as x approaches a from the positive side, and that would be from the right. Okay, and then there are these diagrams. I don't want to talk about those. This is super important. Not only should you have taken note about how to read those coming from the left and approaching from the right kind of one-sided limit definitions, but here you can see everything that we've been talking about so far as pertains to limits. Here we've got the original limit statement that we saw where it's just x approaching a. This one says as x approaches a from the left. This one says as x approaches a from the right. And then there's this super weird thing in the middle that says if and only if. Are they really trying to drive home the point that couldn't they have just put the word if in capital letters? No. What this means is that if this is true, then both of those things are true. And if both of these things are true, then this is true. One implies the other, and the other implies the one. If and only if means that that's always going to be true. It must always be true. If the limit as x approaches a equals L, then the limit from the left and the limit from the right will both approach L. And if the limit from the left and the limit from the right both approach L, then we have permission to say that the limit as x approaches a equals L. I like that idea. They kind of give each other permission. This is a much better graph. Oh, I'm feeling great relief right now. Let's look at question part A. The graph of a function g is shown in figure 10. Use it to state the values if they exist of the following. Okay, so part A says the limit of g of x as x approaches 2 from the left, from the negative side. And I always kind of envision this. One of the other ways that I like to envision this is if there was a person on here and they're approaching an x value of 2, right? Here's my x value of 2, and they're approaching it from the left. What elevation are they approaching? At the moment, this person looks like they're at an elevation of about 2 or 2.1, and they're walking uphill, obviously. You can tell. And they get a bit higher, and they get a bit higher, and they get a bit higher, and a bit higher, and as they get super close to the edge there, as they get really close to that point that has an x-coordinate of 2, what would you say their y values or their elevation is approaching? And I think it's a pretty safe bet to say that they're approaching a y value of 3. So I would say that the answer to this, that this limit is equal to 3. And then let's look at part B. Here it's the same statement. We're still looking at function g, but this is the limit as x approaches 2 from the right. Will this thing slide? There we go. And so I've got my other friend, and they're going to meet me at the point where x equals 2. And so Here they come, and they're approaching the x value of 2 from the right this time, from the positive side, and they're walking, and they're walking, and they're just rolling along, and they get really close, to this point where x equals 2. And look at what their altitude is, so to speak. Look at what their y value is approaching. It's approaching a y value of 1. So we were supposed to meet. When were we supposed to meet? We were supposed to meet when x equals 2. And I'm coming in from the left, and they're coming in from the right, and we've ended up at 2 different places, 2 different y values. We're approaching 2 different y values. 3 from the left, and 1 from the right. Which leads us to this very important question. What is the limit of g of x as x approaches 2? And the answer is, it does not exist. Or, I don't think you would say undefined. I think you would just say it does not exist. Why doesn't it exist? Because the limit from the left does not equal the limit from the right. Because 3 does not equal 1, we do not have permission to say that the limit as x approaches 2 is equal to anything. For options D, E, and F, we have a similar conversation, except we send our 2 friends walking at this point that has an x coordinate of 5. And those y values, those 2 people are actually going to meet, right? They're going to get to the top of this hill, my red self and my purple friend, right? We're going to walk at this point where x is equal to 5, and we're both going to stop before we fall into that hole, and we're going to be looking at each other and looking down into that hole and looking at each other, social distancing on either side of that hole in the graph right there, realizing that we are that's my cat Sophie meowing in the background if you can't hear her. We have reached an elevation or a y value pretty close to 2. We never actually got to the elevation of 2, because if we had pushed it all the way to that point, we would have fallen into the hole. Here's a quiz question for you. Do we care what's actually happening when x equals 5? These limit questions in parts D, E, and F are all about x approaching 5. One's from the left and one from the right, and one's asking us about both. What's going on? Do we actually care what's happening when x equals 5? Absolutely not. I only care what's happening when we're in the neighborhood of x equaling 5. Since our limit from the left is equal to not 5, since our limit as we approach from the left is equal to 2, and the limit as we approached from the right was equal to a y value of 2, can we then safely say that the limit as x approaches 5 is equal to 2? Yes, we can. So that limit exists, and it's equal to 2. And this says everything that I just said, and this says everything else that I just said, and this is a different way of saying we don't care what's happening when x actually equals 5. This says you try it, but I'm going to give you about 1 trillion homework assignment problems on this stuff, so you can try it while you're doing your homework, and you can try this while you're doing your homework. And now let's talk about infinite limits. An infinite limit is not when our x values are approaching infinity. It's that sometimes as our x values get close to a particular number, our y value ends up trending toward infinity. Sometimes it even approaches negative infinity. Different ways of saying the same thing, different ways of saying the same thing. And an illustration finally. Okay, so here's our line, a vertical line, x equals a, right? So this is where our x coordinate is equal to a, and if we hop onto this curve and we start walking to the right, then we end up going drastically uphill, and this blue curve is definitely trending toward x equaling positive infinity, as our x-coordinate gets really close to a. And when we hop on our graph to the right of x equals a and we start walking in from the left, we're going dramatically uphill also. The right-hand side, or as we approach from the right, our curve is going uphill toward positive infinity. Coming at it from the left, we're going up toward positive infinity. Coming at the x value of a from the right, we're going uphill toward positive infinity. So, can we therefore say that the limit as x approaches a is equal to positive infinity? Yes, we can. I love it. Even though it's going toward positive infinity, we can still say that it's equal to positive infinity. There are mathematicians who are also authors who would say that even if you're coming from the left and from the right and both of those curves are trending toward positive infinity, there are people out there who would say, well, then the limit doesn't exist. So infinity's hard to get a hold of. I don't think that we should therefore say it doesn't exist. It's just a little heavy on the conceptual side of things, as is negative infinity. Here you can see that as our blue curve is approaching the vertical red line from the left and from the right, that both of those blue curves are swooping in the downward direction, pointing toward negative infinity. Therefore, we can say, since both sides are curving down toward negative infinity, both of them, we can say that our limit as x approaches a is equal to negative infinity. In neither of the two previous graphs was our function actually defined at x equaled a. That magenta vertical line that the blue curves were approaching, that might as well have been a vertical asymptote. In fact, I wish they had made it a vertical dashed line instead of a solid line, because we've seen asymptotes work like that before, where the curve approaches it but doesn't cross it. I think that would have driven the point home even a little bit better. So, what's in this box, you can read it. It pretty much says what we've been talking about. And so the limit as x approaches negative infinity, after the teachers without bound as x approaches a, an example. Alright, so and then here's an example. Right, so if you take this x value of 0 and you actually plugged it in here, you would get negative 1 divided by 0. 1 divided by 0 is equal to infinity, and there's the negative sign. Are we actually, could we use that kind of language as a proof to indicate that this is equal to negative infinity? No, that was a little too casual. However, it starts you out down the path of understanding, okay? Let's see, similar definitions can be given for, yep, so it's possible for a one-sided limit to equal positive or negative infinity also. Tell me about the limit of f of x as x approaches a from the left. Well, you come over here, you hop onto your graph to the left of where x equals a, and you start following the curve toward that x value of a, and as you're moving to the right, you end up sliding down this graph, and where are you headed? Negative infinity. Therefore, this one-sided limit equals negative infinity. So just a quick example of this one. So it's possible, again, for a one-sided limit to equal positive or negative infinity. These are graphs of infinite limits. These are graphical examples of these four things that we saw on the previous slide. And what do all four of these things, these graphs, have in common? They all have a solid vertical magenta line that I think should be dashed because I think they should be asymptotes. That blue curve is definitely approaching that vertical line, but it does not look like it's crossing it. Every asymptote I've ever seen was a dashed line. I don't know about you. But anyway, graphical representations of one-sided limits which approach either positive or negative infinity. You'll have a homework assignment where you can try that. Are there any good examples in here? I could just give you answers to these. This one's infinity, and as x approaches positive 2 from the left, that one's negative infinity, and as it approaches positive 2 from the right, it goes toward positive infinity. The limit as x approaches negative 1. Both of those curves from the left and from the right go toward negative infinity, therefore we can say that that's equal to negative infinity. Alright, so, cover up the left side of your screen, and, you can't cover up the left side of your screen and then answer those questions. The questions are on the left-hand side of the screen. Anyway, just more food for thought and some examples of one-sided limits, and then also a not one-sided limit. Notice that that one is not a one-sided limit. Oh, this one's not either. As x approaches, let's look at part A. As x approaches negative 3. So here's negative 3. And because part A of question part A here is not a one-sided limit, in order to answer that question, I had to examine my graph as it approaches from the left and as it approaches from the right. And what I noticed is that as I approach from the left, it goes toward positive infinity, and as I approach from the right, it goes toward positive infinity. The question that they should have included in here is part F, which says the limit as x approaches 2. I forgot our function name in here. A of x. The limit of a of x as x approaches positive 2. I'll give you a moment. What do you think the limit of our function as x approaches 2 equals? YouTube's loving me right now. I'm just soaking up real estate. As our x value approaches 2 from the left, our curve dives down, pointing toward negative infinity. As our curve approaches 2 from the right, the curve swoops up toward positive infinity. And positive infinity definitely does not equal negative infinity. And since the limit from the left does not equal the limit from the right, we would say that this limit does not exist. Keep an eye out for those. They're going to happen. There's all the answers. Oh, the equations of the vertical asymptotes. See, I told you they were asymptotes. X equals negative 3, x equals negative 1, and x equals positive 2. The equations of our asymptotes. Super. Definitions, the vertical line x equals vertical asymptote of the curve if at least one of the following statements is true. Yeah, I think that was pretty safe to assume, but you can read through those. It might just make your head hurt. Find the vertical asymptotes of our function f of x equals tan x. This is a pretty labor-intensive process to go through. How did they know to do these tests using pi over 2? I don't know. I mean, I would know to use pi over 2, but I already know where the asymptotes are for the tangent function. I also know when the zeros of the cosine function happen. Both of those would make it very easy for me to choose pi over 2 to do that test. I don't anticipate that you're going to see that very often, that you're supposed to determine the location of a vertical asymptote by testing one-sided limits and seeing if they go toward positive and or negative infinity from both sides. I suppose if you had a supposed vertical asymptote, you could do a bit of a test in order to confirm that it's a vertical asymptote by checking the limits as they come from the left and from the right and seeing if they both equal positive or negative infinity. That would confirm that it's a vertical asymptote. Group quiz. Sketch the graph of an example of a function that satisfies these conditions. that's not the worst exercise in the world. I've seen worse. We're on page 38 already. Where are we going with this thing? Oh, we're going to 39. And the answer's on the next slide. Don't look. Okay, there we go. Let's draw ourselves a little graph here. Just checking what y values I'm going to be needing. 1, 2, 3, 4. 1, 2, 3, 4. And 0, 3. Okay, so this says that do they tell us anything else about the function? No, we don't know we don't know anything about it. Okay, so the limit as x approaches 0 is equal to 1. So with an x coordinate of 0, we're going to have, maybe we don't actually have a point. Well, let's see. So I'm looking at this thing and I'm saying, well, as my x values approach 0, I'll be approaching a y value of 1. And where's that? That would be right here. But I don't know if there's actually a point there. All I know is that my curve, whether it's coming in from here or it's coming in from here, it's coming straight into here, it's going to be trending toward that point. And as my x values approach 0 from the right, we'll be approaching a y value of 1 also. So I don't really know where it's coming from. And then in my head, I thought, well, I don't even know if my function is defined at 0, 1, so I can't put a solid dot there. And look at the top left corner of the screen, right there. The graph does not include a point right there. In fact, this tells us that 0, -1 is actually a point on our graph. So we're going to have a point at 0, 1, and somehow or another, our graph is going to come crashing in to this point right here. But there's going to be a hole there. Hole there, point there, and somehow or another, our graph's going to be coming in here, and it's going to be coming in from that direction also. I gathered all of that from this and from this. These are pretty easy. That's just a point. So let's plot that one over 3 up 1. There we are. And then let's go to this limit right here. As our x values approach 3 from the left, our y value is approaching -2. And that is down here. And now I'm looking at this limit, as our x values approach 3 from the right, our y values are approaching +2. Well, that's up here. So the curve things that I drew in there were pretty arbitrary, except for this part. These two holes definitely needed to be connected, because we were told that as our x values approach 0, our y values need to be approaching 1. We were told that by this limit, and because this limit is not a one-sided limit, and because it exists, that means that the limit as we approach from the left and from the right must be approaching a point with a y value of 1 as we get close to an x coordinate of 0. So that's how I knew to draw sort of this part of the curve coming out of here and a curve coming out of the other side of that hole. And I knew that this hole had to be connected to this hole, one, because there had to be a curve coming out of the right-hand side of this hole, and this limit, this limit said that as we approach 3 from the left, we better be darn near a point that has a y value of -2. And here it is. There, I don't know what symbol that was. Much better. That is a point that has, there's not actually a point there, but it's got a y coordinate of -2. And as we approach it from the left, with x values approaching +3, we are approaching this neighborhood that has a y value of -2. All right, so, watch that part of the video like 6 or 8 times until you can figure out what the heck I'm talking about, but it's all in there, I promise. I'm just a little bit of a spaz right now. Group quiz. That's the group quiz. Hey, look, their graph looks a lot like mine. So we've got our hole down here, we've got a hole right here. We defined this point down here at -1. We defined this point with a y coordinate of +1. We had this hole up here coming out the right-hand side. We came out the left-hand side. They dove down. Anything could have happened in here, as long as it's still a function and as long as it connects from those one hole to the other. That was fun. Let's jump over and look at the homework assignment. We'll see if I can do that somewhat gracefully. 2.2. Homework as a PDF. Just 15 questions. They each have 73 million parts. What is meant by this equation? I think you can explain that now. Is it possible for it to equal 9 even though the limit is equal to 4? You can answer that now. I'm sure of it. Explain what it means to say that as you approach from the left, that equals that. Yep, you can translate that. And explain the meaning of this. Hey, it's an infinite limit. Hey, it's another infinite limit. Hey, it's a graph. And we've got a one-sided limit. Ooh, I don't have a pen active yet. Now it's active. That was actually my finger. It's a limit coming from the left. It's a limit approaching from the right. And then there's the all-important question. Depending on what your answers were for part A and B, can we say that the limit as x approaches 2 is some specific number, or does it end up being does not exist? I leave you to decide. And then here's that question about, is the function actually even defined when x equals 2? Does it matter if the function is defined for the purposes of determining those limits? The answer is no. Am I still interested, just as an aside, if my function is defined when x equals 2? Apparently we're interested. Well, that's a fun looking graph. So you've got some one-sided limits here and here, and then there's the all-important question limit there, and then whether or not it's actually defined when x equals -3. You've got some more one-sided limits. You've got the all-important question defined at that x value, and then round 3 of that same thought pattern. You're going to be a pro at doing that, which is good. And then you've got another function, one-sided limits. You're going to be the kings and queens of one-sided limits. And then here's a word problem. I actually read through this, and I like it. I don't like that my screen looks like it just switched over into some sort of a night mode or something. Can I fix that fairly gracefully? I'm very concerned about being graceful. I'm not really an iPad user. Let's look in here. Light, dark, true tone, night shift. Why does it look like it's on? Off. Ah, that's better. That'll keep me awake. That's not good. How about here? Whew. Super fun. Super fun. You're a professional. There's the word problem. So I like this word problem. This is a decent, like, real world example, and really it's all about one-sided limits. So I'm going to let you answer that one. Here's a piecewise function. You're being asked initially to graph this piecewise function, so just be careful that you're drawing a line on the graph where x is less than -1. You're drawing a parabola between -1 and +1. You're drawing a line with a negative slope where x is greater than 1. You can do it, and then after you do that, there's a follow-up question. There's a limit question waiting for you. This one I definitely wanted to look at with you, because in order to answer this question, you're going to take all of these x values, which you're seeing here, and you're going to plug them into this function, and you're going to generate all of their corresponding y values, and you're going to enter those y values here. And then the last thing that you're going to do is actually finally answer this question. And when you answer that question, you're probably going to be looking... No, you're not looking anywhere in particular. Here... Here your y values are going for your x values, rather, are going from 9.5 and they're getting really close to 9. Here they're starting at 8.9 and they're getting really, really close to 9. So you're probably going to be comparing or examining more closely this y value and this y value, and my interest is whether or not those y values end up being pretty similar to each other or not. And that'll help you determine an answer to this question. I hope you're feeling really bummed right now that you're going to have to take all of those x values and do all of those calculations as part of your homework. I'd like to show you a couple of different ways that you could go about doing all of those evaluations. I'm going to jump into my TI graphing calculator, and I'll show you quickly two different ways that you can do that. One is I've gone into y equals mode, and that's this button in the top left. It says y equals, and I'm going to put in parentheses, I'm going to put my numerator, so I'll put x squared minus 9x, close my parentheses, divided by, open parentheses, x squared minus x minus 72, close parentheses. So I typed this into y equals mode. Maybe it's a little blurry, sorry. And then I'm going to I hit the second button, which is up here near the top left, and then I hit this trace button, which right above the trace button it says Calc. So by hitting the second button and then this button, it gave me access to the Calc function. Excuse me, and once I'm in there, you can see that the very first option, it says value, and I'm going to hit enter in order to select that option, and it comes in and it starts graphing part of my function for me. I don't even know where on the graph that is, but in the bottom left corner of my screen, with all the glare that I'm fighting, you can see, there it is, that it says x equals with a blinking cursor. And at that location, I'm going to type in 9.5 and hit enter. And it says invalid. That's not what I was expecting. Okay, let's take that from the top. I don't even know if this is going to work. I'm going to hit the zoom button, and then I'm going to hit the number 6. I think that's a 6. Nope, that's a 4. There's the 6. And that's going to have the calculator, there we go, draw a graph for me that goes from x values of -10 to +10, which is good because the x values in this problem are between 8.5 9, and 9.5. So those points are on this graph now. Now let's go through that calc routine again. So I'm going to hit second, and then the trace button that says calc above it, and I get the menu where it says value at the top. I'm going to hit enter. It gives me the X with the blinking cursor. I'm going to try typing in 9.5 again and hit enter. Whew, it worked. These numbers are pretty small, but you can see that at the left-hand side of my screen, there's a blinking cursor on my graph. So that's a point that has an X coordinate of 9.5. And then along the bottom of my screen, I see two numbers. In the bottom left, I see the X equals 9.5. And in the bottom right-ish, at the bottom of the Y-axis there, you can see Y equals, and it says Y equals 0.54285,714. We're supposed to be entering our answers correct to 6 decimal places. So that first one is 0.542857. Super exciting. Now I need to enter an X value of 9.1. So I can hit second, and I can hit calc again, and I can hit enter where it says value, and I can type in 9.1 and hit enter, and on my screen it'll show me the X value I typed in and its corresponding Y value. And you do that like 12 times or whatever it is, and you'll be able to enter all of those values. Now, here's option number 2. I'm going to hit second and then the mode button, which is the quit button, and that takes me back to my home screen. I had some other calculations on there, but if I hit clear, it'll make those go away. Now what I'm going to type in on my home screen is the same equation that I typed in to Y equals mode, except I'm just going to type it in right here on my home screen. Parenthesis x squared minus 9x close divided by open parenthesis x squared minus x minus 72 close, enter. And amazing, look at that X value, or look at that Y value. Look at the output that it gave me. It's that same decimal. This is where it gets good. I'm going to now type in the next X value that I'd like to enter into that function. I'm going to type 9.1 on my home screen, and then I'm going to hit this button down here. It's the store button, STO with an arrow on it. Click, and then I'm going to store that in the variable X, which is the same button that we always use when we're typing in a variable into Y equals mode. So I'm going to hit that X button, and it's going to take this number 9.1 and it's going to store it in X. I will hit enter. It's stored it, and now on this calculator anyway, I'm going to hit second, and then I'm going to hit the enter button. Isn't this fun watching me use a calculator? And then second. So look what happens when I hit second enter. It recalled the last thing that I entered into the calculator. And I'm going to leave it there, and I'm going to hit the second button again, and then I'm going to hit the enter button again, and it's going to move up and show me the second to last thing that I entered into the calculator. And it's that equation again. And with that equation on that line right there, I'm going to just hit the enter button, and it's going to process that equation again, except it's going to run it with, oh, we had already done 9.1. Well, that was anticlimactic. Okay, now I'm going to take 9.5 and store it in X and hit enter, and then, oh, I feel like I should do the whole thing again. God, that's so irritating. Well, anyway, now I stored 9.5 in my variable X, and I'm going to do my second enter routine, second enter, and now it's going to process, I'm going to hit enter again, and it's going to process that equation with my other X value. This time it processed it with the 9.5. Previously it processed it with the 9.1. So you type yourself in a number like 9.05, store, X, enter, second enter, enter again. And just keep processing those different X values through the same equation by recalling the equation. I think on the TI-85 or the 89, you can just hit the up arrow and it'll go up, and you'll be able to hit enter and reprocess that expression with the x squared minus 9x, etc. Whew. I was thinking about having a coffee. I don't think I need a coffee. How are we doing? Okay, so you're going to enter all those. You're going to answer that question. Use a table of values to estimate the value of the limit. Yeah, that'd be probably a good idea. You don't want to take a 1 and plug it in. Oh, you can't see it as well as I can. There you go. In number 10, you don't want to take a 1 and just plug it into here because you're going to get a 0 in the numerator and denominator. Indeterminate form, not good. So a table of values would be good. Should you use this many values? Please don't use that many values. Not unless someone with PhD after their name tells you to. Or MS, I suppose. Maybe even an MA. MS, PhD for sure though. I've used 2 values on the low side, 2 values on the high side. See if you're trending toward the same y value. If they're trending toward the same y value as you approach from the left and as you approach from the right, then type in whatever y value it's trending toward, and that will be your answer for the limit. Number 11 is a tutorial problem, so that's going to be an interactive problem when you're actually online doing it. Determine the infinite limit. So we want to know if this one's going to positive or negative infinity. And you know how you're supposed to do this. You could do it with a calculator, and you could evaluate this expression or this function using a number, and as x is approaching 9 from the left means you would want to use an x value like 8.999. That's a little bit left of 9, and you could just plug that x value in, and that would be that would give you a rough idea of the neighborhood that you're going to end up in if you actually got to the point where x equals 9, which you don't want to do because you'll have division by 0. So you could do that, or imagine you're using 8.999. It's a little bit to the left of 9. Take 8.999 and plug it in for x. You've got e, which is like 2.7, raised to the power of almost 9. I don't know, 2.7 to the 9th power. I don't know. Type that into your calculator, see what you get. Use e, punch it into the calculator, see what you get. I don't even really care about it. 2 to the 9th power. It's going to be like close to, it's going to be bigger than 1,000, or roughly 1,000. What happens when you take 8.999 and put it in here, and then subtract 9 from it? 9, oh, that's backwards. 8.999 minus 9 is going to give you 0.001. That's a really small number. That's 1,000th. And what happens when you take 1,000th and you cube it? You get a billionth. 0.00. Okay, you get the point, right? It's like 8 zeros and then a 1. It's an insanely small number. And what happens when you take a number like 1,000 and you divide it by a number that's really small? You get a number that's really big. Oh, I should point out, I made an arithmetic mistake. This is negative 0.001. What happens when you cube a negative number? You still get a negative number. So using this example of a value that's pretty close to 9, but it's a little bit to the left of 9, you end up with approximately 1,000 over negative 0.123456781. A medium-sized number up here divided by a super small number down here is going to give you an insanely large number. This would actually turn out to be 1 trillion, except it's going to be negative 1 trillion. So what do you think? You think this limit's approaching positive infinity or negative infinity? I leave it up to you to decide. And I have to finish this video one day because I have 4 other videos to make. and it's late already. Determine the infinite limit. Look up the graph of cotan, approach the asymptote from the right, see where it's headed, take whatever number that is. It's either going to be positive or negative infinity, multiply that by 2 pi, and you should be able to decide on that one. You also have probably taken a pre-calculus class or a trig class, so you should be able to just remember what the graph of cotan looks like. In the theory of relativity, this is another great question. It's a lot like this question. You can just kind of rough your way into this one. Velocity, it tells us over here to the right, is approaching the speed of light from the left. Okay, what's the speed of light? I don't know. I will concede that I do not know what the speed of light is. It's fast. How about that? So your velocity is approaching the speed of light from the left. Let's say that the speed of light is 100 miles per hour. It's a lot faster than that, I know, but it doesn't matter. And if the speed, if your velocity, v, is approaching the speed of light from the left, then if this is your c value, then your velocity value might be 99.999. Okay, so they're really similar to each other. And then in this equation up here, we see that we have v squared divided by c squared. Well, you've got these two numbers that are almost identical. When you divide them by each other, what do you think you're going to get? Something pretty darn close to 1. Maybe like 0.9999999 or something. And then what happens when you take the number 1 and you subtract 0.9999999? You're going to get a number that's awfully small. And as v gets insanely close to c, the result of doing this arithmetic underneath the square root symbol is going to yield a number that's like insanely small. Small like that kind of small. A decimal point and then 50 zeros and then a 1. Okay? And then you take the square root of that and you've got a decimal point with 25 zeros and a 1. And then you're going to take the mass of your object and you're going to divide it by a crazy small number. What happens when you take some reasonably sized number and divide it by something that's insanely small? You decide. And guess what? There's more. I thought I was going to roll off the bottom of the page and we were going to be done. My longest video yet. Sorry to drag you through this. Well, you don't have to stick around. You could have left an hour ago. Use a graphing utility to graph this function. You're welcome to do that. If you don't have a graphing utility, I apologize for all the TI graphing calculator stuff. You're just going to have to do it manually on your scientific calculator or your abacus or whatever you have access to. If you're using a computer, which you clearly are because you're watching this video, you can take this function and plug it into Desmos, DESMOS.com. That's a free graphing utility, so that at least you can check this out for yourself. Unless you want to plug in a handful of x values and calculate y values and plot points and see which one of these graphs is the correct graph. After you've chosen the correct graph, hey, as x approaches 0, your function is oscillating, which means going back and forth between -1 and +1. That's one answer option. So the question is to describe the behavior of the function as x approaches 0. If this is the right option, then you're doing the old split routine, which means your limit would be undefined, and here your limit would be undefined, and here they're doing Splitsville, undefined as x approaches 0, and then here, as x approaches 0 from both sides, your y coordinate is approaching 0, because you're going to be at the origin. Right, so that should be helpful. Determine the behavior of the function as x approaches 0. Yep, you can handle it from there. Hey, thanks for hanging out with me for an hour and 10 minutes if you made it the whole way. You're amazing. I was just confirming that that was actually the end of the homework assignment. So that was a lecture and a tour through a homework assignment. I hope it ends up being beneficial to you, and I will see you on the flip side.